snacks and drinks and get settled. We'll get started very soon. So with that, so our meetup today is our Mark. He's from NVIDIA. He's gonna talk about his recent cool research he's doing, how he's applying machine learning to his domain. So we'll hear from him. Our sponsor partner today, Spark Cognition, been very generous to us. So we've been sponsoring many of our meetups. So with that, I would like to give them a big hand of claps. Thank you. Yep. Thanks. So Spark Cognition and the Venue, obviously Capital Factory, they're sponsoring our Venue. And recently we got the 501c approval. That's a big step for the way we are running this meetup, just to reach out to the community and outside the community if possible. So this was a big step for us. So we're very glad we got this milestone. So our meetups today, obviously, we already discussed. Couple of other meetups also sponsored by Spark Cognition coming up. And do look up our meetup group for other meetups that will be setting up, but not yet decided. But these are the currently what you know. Okay, so a little bit correction, I should have noted it. We had to change the number. I think it's one of the Thanksgiving Day. We moved it earlier, and please note it in our meetups group page, because we had to also shift the time. So keep making note of that. Interesting talks coming up. So, and with that, I'll first. So our invited speaker, Mark. I know him from working with him in IBM. He's been there for a while, then moved on to different and better places, and now he'll discuss what his research is currently and how he's applying it, machine learning, to his immediate work. With that, I would like to invite our sponsor, Spark Cognition. They will introduce us to their cool products and see what's going on there. Perfect. Thank you.
Perfect. There we go. Super. Thank you. I'm Randy Groves. I'm VP of Engineering and Data Science out of Spark Cognition, and we're thrilled to be a sponsor for this meetup. Just to give you a quick overview about what we do so we can get to the exciting stuff in a little bit, but we are a company that's focused on doing artificial intelligence for industrial applications. So we focus on helping our customers secure, optimize, and predict failures in their systems and make sure that they can keep them running efficiently, effectively, and using artificial intelligence to really capture that what's almost tribal knowledge that people have for running all of these large pieces of equipment, many of whom are retiring or whatever, or hard to train and maintain, and capturing that with artificial intelligence. And my laptop decided to slip down. All right. Just quickly, some of the industries we're in, like I said, focus on industrial applications, big power plants, oil and gas, transportation. You may have seen that we've got a joint venture with Boeing as an example, so we also are involved in defense and finance. And the kind of applications that we focus on are predictive maintenance, decision support, workflow automation, robotic process automation kind of things. We've got some cybersecurity, endpoint protection, our Deep Armor product, as well as process optimization work. As part of that, we actually have 4 products that we develop. I'm not going to talk about all of them, but just to give you a quick highlights of the 4. Spark Predict is our first product, and it's the one that works to predict, provide predictive maintenance on large pieces of equipment, helping customers know when their combustion turbine maybe needs to be taken offline and repaired, as an example, but it also applies to aircraft and other kinds of applications. A companion to that is our Deep NLP product that is able to sift through maintenance logs and maintenance manuals and actually help recommend the kinds of repairs that should be done when Spark Predict says something's going wrong, but it's also used for a lot of other natural language processing techniques where you're basically trying to take any kind of unstructured textual data and turn it into structured data that you can build a model on. I mentioned briefly also our endpoint protection product, Deep Armor, which basically uses artificial intelligence to detect zero-day malware. So we're able to to determine a piece of software is malicious without ever having been seen before, which is obviously very important compared to the traditional signature-based approaches, which are often exposed for several days before everybody gets updated. And then our newest and most exciting product, probably to this audience, is our Darwin product, which is our automated model building that uses AI to build AI. And I will, focus on it not only because of the audience, but we also have a new version of it coming out on Monday, our version 2.0. So if it'd be a good time to pick it up and use it. But it really it helps go through the whole process of optimizing and designing your models all the way from data ingestion to model building and then, of course, being able to run those models. And the key thing is with neural networks, a lot of older techniques, do a lot of hyperparameter optimization in order to optimize their models. When you get into neural networks, you have an additional complexity is there's an infinite number of architectural options that you can go through as well. And so we use genetic algorithms to help search through that space and come up with an optimal architecture as well. And hopefully this video will play and you'll be able to hear it. Gives just a quick view of what it's doing. If I can get that button.
Darwin accelerates data science at scale by automating the building and deployment of models. In Darwin's productive development environment, data scientists with a broad spectrum of experience can rapidly create models by simply selecting the kind of problem they are trying to solve, uploading their data set, and specifying training parameters. Darwin uses a blend of patented evolutionary algorithms and deep learning methods to automatically clean the data, implement feature engineering, and iterate through thousands of possible model architectures to find the optimal solution. With support for both supervised and unsupervised training, Darwin enables quick prototyping of use cases for accelerated development, tuning, and implementation of models. It also makes models explainable by providing insights on how these results were achieved. Once models are created, additional data sets can be used to either test or improve model accuracy, automating the model maintenance process. Darwin includes a Python SDK and REST API, offering full control of the process and facilitating integration with third-party solutions. Darwin augments your in-house talent by making machine learning accessible and scalable. Darwin, accelerate data science, solve problems at scale.
So just real quick to give you a sense of how it fits in the overall data science process. Data science obviously spends an awful lot of time collecting the data, curating the data, and getting it into a form that you can actually build a model. From that point on, as Darwin focuses on actually accelerating the development and optimization of models and deployment of models. We're going to continue to expand its capabilities, but that's where we're at today, and we're very excited about the new version that's coming out next week. So, not going to spend a lot more time on it. If you have any more questions, you can come up and talk to me afterwards. You can also obviously go out to our website and read some of our white papers. I did also want to highlight, we have our own conference. This is the third year that we'll be having Time Machine. This year we're moving to the Palmer Event Center. It's been a big success. We've got a lot of very exciting speakers, including the former CEO of Cisco, John Chambers, the former founder of 3Com and one of the inventors of Ethernet, Bob Metcalf. We have Dr. Bruce Porter from the Computer Science Department at UT, Secretary Work from the Defense Department, and a whole variety. If you can find out all of the various speakers by going to the website. I will tell you that it's not a very technical conference. It focuses a lot more on applications, policy, and customer use cases. There's obviously talking about using AI in all of those cases, but it's not somewhere where you're discussing algorithms or Python coding or any of that kind of stuff. But if you're interested in that, it's a very fascinating environment and a chance to see some good speakers. And I have these brochures that have a special discount code for you that I have up here, and there's some also back there by the pizza if you're interested in going. So encourage you to attend that as well. And again, thank you very much for coming here tonight, and we'll turn this over to our host. Thank you.
Thank you, Andrew.
Hi. Okay, good evening. My name is Mark. I work at NVIDIA, and my job is as a research scientist is to figure out how to build a novel way of building chips, right? Because NVIDIA is building chips, and the machine learning is one of the techniques that we are looking into how to build better chips. Before I talking about going to my presentation material, we will ask about the company to talk about our some products we offers. So actually, just a quick question: like, how many of you actually are very familiar with NVIDIA's products? Very familiar. Okay, pretty much, right? So I'm just go through this really quickly. Basically, NVIDIA is making a lot of accelerated computing products. So basically, we are seeing that the computing power sort of saturated over the last several years, but I'm talking about the CPU. But the GPU computing is actually going through at a higher acceleration speed. So we're trying to solve these computing problems. And so we basically have a lot of new products like Turing, which has new features like Tensor Core and RT Core, ray tracing cores. Okay, we can do a lot of visual stuff. So this is RTX ray tracing. Actually, I'm very excited about this, like supercomputing kind of stuff. Let me see which one is I'm trying to talk about. Yeah, this one, right? So DGX, right? This is many GPUs inside of one box can have a supercomputing power, and it's not that expensive. And actually, recently, all the MLPerf results are trained on either single DGX or multiple DGX. So we also have things like, I'm just go through this, yeah, Xavier. This is our SoC that's actually can be used on autonomous cars, like good for autonomous driving. And these are not small chips. They are half rectangle size chip, more than 300 millimeters size. So kind of like larger server chips, but they are actually SoCs. And we also have some very smaller ones like the Jason, which is like this size and can be used on a lot of IoT kind of AI projects. Okay, so let's done this. Okay. Play from start. Just hit the play from start, right? Cool. Okay, thanks, Tuki. All right. Yeah. So today I'm going to talk about how to use machine learning to help chip design automation. First, like, how many of you are actually, familiar with chip design, especially digital circuit designs? Okay, that's good. That's good. So that makes my job easier because I saw like this is a big data community, and maybe I have to go from the basics, like about how to design chips. But all right, so this is my outline. So I'm gonna still talk about a little bit about what design automation is, right? And then I will introduce several applications of using machine learning to design chips. Some of these applications are the research projects that we were doing. Some of them are other research groups' contributions. And that will give conclusion at the end. Okay, so let's start with design automation. So for those of you that are not really familiar with how chip is designed, basically the process is like we have design engineers that has ideas, and they write code, right? We call it RTL or System C, and then the design automation is a set of tools and flows that's going to convert these codes into layout, right? So on the right is the layout of the Xavier chip I just mentioned. So it's like a compiler, right? If you are familiar with the software, so let me show you like one design automation flows that we use for digital circuit design. Basically, there's a design specifications that you want, the design you want to implement, and the design engineers is going to write, basically, write it into code. So you can write in high-level languages such as System C, or you can write in low-level languages such as RTL, which is very lucky in the US. If you write in System C, you can use high-level synthesis tool to basically compile that into RTL. And then we'll use a synthesis tool to convert the RTL back to actually to gate level netlist. So at this time, it's no longer a code anymore. It's a netlist with gates. And then we run physical design tools that's going to basically create a layout. Right? Layout means gates are placed in a die, like the rectangle things that you just saw. And then this layout will be sent to manufacturing companies such as TSMC, and they will make wafers, and the wafers will be dissected into dies and packaged into chips, and then we'll test it as well to make sure it's actually working, right? And then those pass the test will be shipped to customers. So so in addition to the main flow, there are also a lot of things going on. For example, you have to check that the RTL that you implemented is actually doing the things that you really wanted to do, as the same as your design spec, right? So that's called functional verification. And then because the newer technologies is very difficult to manufacture, so when we're doing the physical design, when we're doing the layout, we need to make sure this layout can be actually manufacturable. So that's called a manufacturability test. And then, of course, we need to make sure that the designs are testable by the test machines. That means you also need to make sure when you generate the design, those circuits can be tested. So that's testability problems. The reason I'm mentioning, to give you the high-level pictures here is I will actually show you applications in some of these areas. And when I talk about those applications, now you'll have an idea of what it's actually talking about, in the overall design flow. Question?
So say you come up with new hardware one year. Are you rewriting the programs, or are you changing the compiler?
Good question. Yes. So of course we're writing new program, right? New architectures, new ideas, right? Because the chip design industry has many players. So NVIDIA is a design company. So design company basically most using the tools, right? So using these design automation tools built by other EDA companies such as Cadence or Synopsys. So when I talk about the tools, most of the tools are built by those companies. But we also have many engineers working on how to build a system, like a system of tools. We call it flow, to basically our own design methodologies are implemented with our own flow. So basically, it's like if you have a PyTorch, that's the tools that EDA company provides you as a tools. But you write your own model, right? You write your own training model. So it's the same kind of analogy here. So the design company has to write their own flow based on the functionalities provided by EDA companies, the tools they provide, the softwares. And in addition to that, they might choose to write their own in-house tools, just because sometimes the other tools is just not capable of dealing with the chips that they want to design. Okay. Okay. So why we are talking about design automation? Because right now there's like a two macro trend that I'm saying. First is the end of technology scaling. Right? So everybody familiar with Moore's law. So you know that the Moore's law is actually ending. Right? Transistors cannot double in every 1.5 or 2 years. It's not happening. And also there's the Denali scaling, which basically saying that power equals to CFV square, which means if you reduce your voltage by half, you can actually increase your frequency 4 times, right? 4 times, where you can maintain the constant power. So that law actually helped us to see CPU performance increase, like the frequencies increase exponentially kind of through the years. But that law was broken since 2005, right? Because leakage power and other things that just you cannot maintain a constant power with a high frequency. So that means to get a better design, how do you do? Right? You cannot just say, let's wait 2 years and build a chip with a high, better technology. Like for example, like today's like AMD's 7-nanometer chip compared to our 12-nanometer chip, right? So you cannot say that 7-nanometer chip is better than 12-nanometer chip just because scaling. It doesn't help that much. Now, so what people do is they have to come up with better design ideas, right? Build a smarter design. The other way they can do it, actually increase their performance, is by have a better design automation, right? Better compilers, right? So because there's a lot of margins on these automatic tools that you can squeeze and actually produce better results for you. And the second macro trend is the rising design cost. So as this graph shows, in 14-nanometer, right, on the right-hand side, the design cost is like $100 million, right, including design and the verification. $100 million. So not many people can do this anymore. So to reduce the design cost, what do? Right? You increase the productivity, right? If you need 100 engineers to build a chip, if you increase the productivity by twice, then you only need 50 engineers. But how do you improve your design productivity? You can build a better design automation, right? Let the machine do the job for you. Okay, so now we have a opportunity, right, which is the machine learning. And we know that machine learning have achieved greater success in various areas, like in image recognition, in AlphaGo playing, in autonomous driving, and in language processing, understanding, language recognition. So the question is, can we use machine learning to improve the design automation such that we can get better quality results and better productivity? Right? So that's the question we're trying to address today. Okay, now let's talk about applications. So in my mind, I think there are 3 major categories of applications that we can do with machine learning for design automation. There are prediction, generation, and optimization. And they line up well with the classification of machine learning algorithms, such as supervised learning, unsupervised learning, and reinforcement learning. Right? So let's start with prediction first. So prediction is basically trying to predict some results that you're not sure of, right? So in the design flow, there's a lot of places that we can use the prediction. And to do the prediction, basically we do supervised learning, right? Based on the design data, we know what's the labels for that prediction, and then we train a model such that when we see new data, we can predict their labels. And here I'm going to introduce 4 applications, 4 test case scenarios. This basically first one is a DRC prediction with classical machine learning methods. Second is power prediction with convolutional neural network. And then third is DRC hotspot prediction with fully convolutional networks. And fourth is testability prediction with graph convolutional networks. And let's start. So just mention one the difference between classical machine learning and deep learning, right? Because I made a difference here that the first project is using classical machine learning, and the rest of them are actually in the deep learning category. That we know that deep learning usually give you better results when you have a large amount of data, right? So in the chip design, we usually have a large amount of data because the chip is very complex. Another benefit is for deep learning, we don't really need a very sophisticated feature engineering. So that's also very helpful. So the first application is to do congestion and DRC prediction. So let's just briefly introduce this problem first. Like I said in the previous slides, when you have RTL, which is the code that you want to do the digital design, you run through synthesis and the physical design and generate a layout, right? So during physical design phase, there's maybe three major steps. First, you place all the gates on the layout, and then you do some optimization, and then you have to route it, right? To connecting the gates with wires. Oftentimes we found that it's very difficult to route. So if you look at this layout image, you can see there's some red spots. Those are the congested areas. That means basically routes going through that area will basically have very difficult to put all those wires going through those areas, which will result in DRCs. DRC means design rule checking errors. That means it's not manufacturable, right? So the manufacturing companies, they design some rules and say, you cannot put the two wires so close, right? Wires has to be far away from each other. And those kind of DRC, called the DRC rule, DRC checks. And if the routing is congested, it's very easy to violate those DRC rules, causing DRC violations, which means the chip is not manufacturable. So usually, the designers only knows the DRC violations after the entire flow is finished, right? Only after they have the layout netlist. You have to route it first. But if we go through the entire process and then come back to fix it, it's just too slow. So usually this process probably take a few days, even with today's very fast computer. So what I mean is like going from synthesis all the way to layout netlist on a sophisticated design. It will take a few days. So here, if we can predict the congestion really early on, like in the placement stage or even in the synthesis stage, then we can do something about it to relieve those congested areas. So that's why we need this prediction, right? So basically, we want to predict the routing congestion at early design stage. So the approach is, this approach is using classical machine learning, such as like SVM kind of approach. So usually you have input features and you have output labels. So here, what's the feature? In this work, they take a window-based approach. So they divide the entire layout area into multiple grids. And for each grid, they pick a window around that grid. And then they collect some information from that window, right? Information such as like pin densities, cell densities, global routing resources, pin proximities. So those are the information that's readily available at early design stage without going through detailed routing. So they take that information within that window, and they basically build a data set, right? And the data set will have labels that basically after detailed routing, they know, okay, in this on this grid, there is some DRC violation, there is some congestion. So they can build a data set to match that. And this way they can directly predict the routing congestion and DRCs. So this is the results. On the left is comparing a global routing-based prediction versus this SVM-based prediction, right? So there are very simple global routing algorithms that you can use to predicting routing congestions. But in this picture, it's saying that it's not as close as the SVM-based prediction. So the red dot here are the spots predicted by global routing, but the blue dots are the real DRC errors. So we can see that the global, if you just run a global routing algorithm, it doesn't give you very good prediction because the red dot and the blue dot doesn't match. However, if you use the SVM-based approach, looking at the features in the nearby windows and trying to predict the DRCs, the predictions are more closer, more accurate. Okay. Another prediction kind of project is about the power. So the power consumption of chip is very important. So usually the design team will do a lot of power simulations to estimate the power consumption of the chip they design. Typically, this is done on a gate level netlist, which have millions of, hundreds of millions of gates. So that kind of power simulation runs very slow. Usually it's like 10 to 100 cycles a second. That means if you need to run some applications, get the entire power trace for the application, it will take a very long time to generate the power estimation. But it's very accurate. Now, you can also estimate the power at the higher level. For example, you can estimate the power at the system C level or RTL level. At those levels, the simulation runs faster. So you get your results faster, maybe at 1,000 or 10,000 cycles a second kind of simulation. But the downside is it's not very accurate because it doesn't have the information of the netlist. It doesn't know which gates is going to consume power. It only knows the RTL code. So the goal here is to see if we can use a machine learning model to predict the gate level power from the system C and RTL simulations, right? Trying to bridge these two worlds, taking the benefit of both. So now you can see the speed of the model is very important. That's why we investigate fast CNN techniques. So over the years, people have developed many CNN models, and some of them have a lot of parameters. Some of them have less parameters. So if you plot them on the basically x-axis is the computing complexity of the number of G-flops, and on the y-axis is the accuracy of the model on the ImageNet. Then you can see something like this. So ideally, we want a fast model to be on the upper left-hand side, right? The higher to the upper left corner, the better, which means the smallest computing complexity with the highest accuracy. Now, we found one model called ShuffleNet V2, which sits nicely near the upper left corner, and so that's the model we want to use. Okay, so how did it work? Basically, given the netlist, you have, let's say in this example, we have 5 registers, A, B, C, D, E, and we have gates connecting them. Now from the RTL simulation, we know the traces on each registers. So we know the A, B, C, D, E, and their values through time. So here we have maybe 3 cycles. So you can see the A, B, C, and D, E have different values through the time. Now, basically, we want to predict the power at each cycle, right? Based on these traces. And on that picture shows that we have a ground truth of power, and we have this predicted power. We want to see the ground truth and predicted power are close. That's the goal. Okay, so how do we leverage the CNN model we just mentioned? First, we have to convert that trace file into an image, right? Because we're talking about image-based CNN model. So we have 5 registers. That means we need to somehow create an image with that 5 register. So we can create a 3 by 3 image, right? 3 by 3 element image And we can map that A, B, C, D, E registers to pixels on the image. Okay, so that's how we map it. And this image CNN has 3 layers, RGB. In this case, we actually map the switching activities of the each registers into 3 channels. So a register can either stay constant or switching from 0 to 1 or from 1 to 0, right? So we can create 3 channels to map that activity. So that's kind of like one-hot encoding on these channels. So now we have images of 3 channels. Then we can run through the ShuffleNet V2, which will generate one number, and that number will doing a regression loss with the actual ground truth. So now we have a model to predict the power traces, powers directly from the trace. And here's some results, right? So we're comparing the CNN-based methods with classical machine learning methods, such as XGBoost, linear regression, or even MLP. Also, within CNN, we choose to we run several variants of the CNN, not on the model itself, but on how we map the traces into images. Basically, how we do feature engineering. So we have tried 3 different ways of mapping the registers to the image, and we found that the CNN-based method has a better performance, better accuracy when the design is large, right? So if we look at the all those designs, there's adder pipelines or multipliers, RISC-V cores. We see that on the smaller designs, basically all this, except for RISC-V cores, everything else is relatively small. The performance of a classical machine learning-based model and the CNN model is similar. However, on the RISC-V core, which is much larger than the others, we can see the CNN-based methods outperform all the other classical machine learning models because they have better complex. And also, if you look at the variance of CNN models, they don't vary much. So it doesn't matter how I encode that traces into images. The results pretty much the same. So we should also prove the notion that you don't really need to do a lot of feature engineering with deep learning models. Okay, so another model is the problem that we're trying to solve is also related to DRC, but here we are trying to predict the hotspots. So basically, given images of the layout, we want to predict where the DRC hotspot will be. So these images can be pin density map, macro placement map, some sort of global routing estimate. We call this RUDI. It's just a simple global routing algorithm. So with these inputs images, we want to see, can we directly produce an output map that can predict which area has DRC. So here we leverage this model called fully convolutional networks. The difference between this network and the CNN is it has this upsampling layers that can increase the dimension of your activation layers. So basically, starting from an image like a cat's pictures on the left, it does convolutions to reduce the image size, and then it does the upsampling, we call the transpose convolutions, to increase the image size. So at the end, you can also generate an image, right? So it's from image to image, and it was proposed to do image segmentation kind of work, and we think we can leverage this model to basically trying to predict a hotspot map right? So given a input layout, can we produce a DRC hotspot map at end? So this is the model we have. Basically, it's just doing the exact same thing in the last slides. We take an input image with W times H pixels, and with convolutions, we reduce and pooling, we reduce the size of the image to 1/4 of W. And then with upsampling, we come back to the original image size. And the loss function is basically just at output, we know where's the DRC, we know the labels, so we just do a regression loss on the output. So here's some results. So in the center is the ground truth. So those are the hotspots, ground truth. On the left side is we use the method we talked at the beginning, the window-based classical machine learning approach to predict the DRC. They can predict some of the hotspots, but they also create a lot of false positives. On the right-hand side is the round net, which actually predict the pretty well that the hotspot is correlated well with the ground truth. And the reason is the window-based approach, it doesn't see the entire image. It only sees a local window. Now, in this design, they have a lot of big macros that span across the window. So the window-based approach cannot even see those information. Now, with this fully convolutional neural networks, each pixel is able to get the information from neighboring or even far away pixels. So that's why the prediction is more accurate. Okay, now I'm going to talk about some problems in testing. Oh, sorry. Okay. Right. So there are ways for you to manipulate the design. So let's say if you know that this area is congested, what you do is you like creating some expansion factors for the cells in that area. Then it will just pushing cells away from that area. And these can be manipulated by design team or by CAD tools. So either basically the design team can have a script to do this, or the CAD tool can provide features to do this. So it's once you have the methods, it can be implemented by both the EDA companies or design companies. Right. Right. So you train this model offline, right? So you did a lot of placement routes. With that data, you produce this model. Once you have the model, then when you have a new design, you can just do inference. You inference this to get the congestion map, the DRC map of your new design, and then you can do something very early on, right? Not until routing finish, DRC checking it down. Okay. Yeah.
What does the image look like that goes into that model? Is it like all the components, literally like a camera shot, or is it some other representation that you create?
Yeah, so it is basically, it's not a camera shot because it depends on the dimensions. So if we have 1,000 by 1,000 dimensions, but the chip image, if you look at the layout, is a much larger dimension than that. So we'll actually creating features for each grid. So it's like aggregating information within that particular grid, and that's my features inside that grid. So I don't know if that explains well. Basically, if you can think about that image's dimensions maybe 1,000 by 1,000, and within that each grid, so each grid of that 1,000 by 1,000 pixels, each pixels of that 1,000 by 1,000 images is basically some rectangle areas on that chip, and then you have to search for all the cells that actually sort of overlap with that small rectangles, and then collecting the features from that small rectangle and put it on a put on a pixel. Make sense? All right. Okay. So, oh, one more. Yes. So it is based on the let's see. Yeah, you can see this is. So we have 4 channels for this model. So there are pin density map, right? Pin density means in that rectangle area, how many pins are there, right? Macro map, whether there's a macro on this rectangle. Long-range RUDI and RUDI pins, those are just some global routing estimates that actually passing through that rectangles. So, I mean, you can create your own features, but this is basically collected features. Okay. The reason I want to talk about testing is because I want to introduce a new model. And it's a graph-based model. I think it's a very exciting model to use in the chip design area, chip design related machine learning projects. So just a little bit overview of what's chip test, how do we test the chip, right? So basically, if you think about it, a chip is accepting some inputs and generating some outputs. So the way we test it is we send a whole bunch of inputs to the chip, and then we check the output, right? And we're trying to match that outputs with my golden set of outputs. If they match, that means it's a good chip. If it doesn't match, it's a bad chip. Right? It's a very simple way of explaining what testing is. So what will happen is if there's a failure on the chip, for example, some nets get stuck at 0, some shorts happen in the layout, that this signal just always 0. It's not going to turn. Then if you apply some inputs, the outputs might changed, and then it doesn't match your golden outputs anymore. So you know that's a failed chip. Now there's some problem because not every signals on the chip is testable. I can show you like one very simple example. Let's say you have this kind of circuits. Now if you look at the output of A, right, that gate, it's going to be almost always 0 because the function of the gates is depend on an AND function of a lot of inputs, right? So basic Boolean logic, you know that it's very difficult to get A to be 1 because it requires every input to be 1, right? So that's a very low probability to have every input to be 1. That means the outputs of the circuits O will always be 0, because if one of the A is 0, then the output of course is 0 because it's connected by AND gates. So now there's a problem because if I have a stuck fault at the B, that fault cannot be observed because it doesn't change output, right? Doesn't matter whether my B is 1 or 0. As long as A is 0, my output is always 0. So I just cannot observe this fault. So this is called a difficult to test points on the design. And the way people handle this is by inserting actual registers on this particular point. So you can actually observe this point directly. So the problem is trying to estimate, where is this difficult test point. Which we have some algorithm to estimate it, but take a long time. So we're thinking, can we use machine learning algorithms to estimate where are the difficult test point? So basically, given us a netlist, can I use machine learning algorithms to estimate which signals, which nets in this design is a very difficult test? Right. So that's basically the problem, and we have input features, and these features are things like logic level, which is how far away are these gates to the inputs. It could be 1 level, 2 level, 3 level away, and then we have scope values, And these are just very simple algorithms that compute the controllabilities and observabilities of the circuits. I don't want to go to detail and explain these algorithms, but it's just a very simple algorithm that you can run and get some number that can use as the input features. And then the output is we want to predict whether if we can classify that which node is difficult to test or not. And those labels can be generated by some TetraMax, which is go ahead. Input probabilities. No, this input features is based on the circuits you have. So given your circuits, I can generate the input features. No, that's not it. So each inputs. Okay, sorry. I think I'm probably misleading you. When I say input, I'm talking about the input to the model, to the machine learning model. So the features are on each gate. So on each gate of the design, we have 4 numbers, okay, as the inputs to the machine learning model. Okay, now let's talk about the graph convolutional networks. And basically, it's called GCN. It's neural models to handle graph. What it does is basically aggregating information from neighboring nodes, as shown in this animation. So compared to the CNN, right, which actually does this kind of aggregation on neighboring pixels, right? So they have these kernels that run on a window. That's basically, aggregating information from the neighboring pixels. GCN is aggregating information from their neighboring node, right? Once the information are aggregated by either a min function or sum function, they will apply a encoding step to map the feature space from low dimension to a high dimension. And also you can apply ReLU functions as well. So that's called a 1 GCN layer. This is the math for this layer. For our problem, right, we are given a circuit. We map that into graph. So each node in the graph is a gate, and the edges are the net connecting the gates. And then we can go through this GCN layers, maybe 3 layers. And at the end, we'll have node embeddings on each node. And then we can apply fully connected layers to predict whether this node is testable or not based on our label. And initial labels on each node is just the 4 numbers I talk about, logical levels and the 3 scope values. And this shows the prediction accuracies. So we can see that the accuracies improves when you have, of course, more epochs, training epochs, and also improves when you have more GCN layers. So k equals to 3 already give you like 90% accuracy. And on the right-hand side, it's comparing GCN with other machine learning models like random forest SVM. And you can see that the GCN model applied to this model, applied to this problem, have much higher accuracies than the other models. And with this model, we were able to produce our own test point insertion flow that actually did a better job than the commercial tools. So we can have much less number of test points inserted with this prediction model. And then we think the graph model is very common for a lot of design automation problems. And I think it will be useful for a lot of other areas as well. Okay, now I think we covered the prediction problems pretty well, and I'm going to switch gears to about the generation problem, optimization problems, basically unsupervised learning and reinforcement learning. These are still new areas for design automation, so we don't have a lot of works in this area, but there are some interesting works that basically shows the benefits of applying unsupervised learning and reinforcement learning. So the first project is called OPC mask generation with generative adversarial networks again. And the second project is called logic optimization with reinforcement learning. So for the first problem, the OPC problem, let me just briefly talk about the problem first. So on the advanced technology, if you want to build a rectangle, right, you cannot just build a mask of a rectangle, because if you build that, the lithography will generate a shape like a bowling pin, right? So it's not going to be rectangle anymore. So what you do is you do something called optical proximity correction, called OPC, that's going to add extra shapes on this original rectangles, such that after lithography, the silicon image will look like a rectangle. So how to generate this OPC layout? Usually people, what they do is they have a target shape. Then they use something called the inverse lithography transform, basically trying to inverse the lithography equations to compute the shapes that is required to actually generate the real shapes on the wafer. So that's a very computation expensive task, usually taking hours or days or kind of computing power. So this work is trying to leverage GAN. So I guess many people know GAN. Basically, there's a generator and a discriminator, right? So the generator will take in random noise and generate an image, and the discriminator will try to identify which one is the real image and which one is the generated image. So over the time, the discriminator is so good that the generator has to generate real images that like the real image. So here, basically, we want to use this generator here to directly generate the OPC mask from the target. So that's this work is trying to achieve. So given a task image, given a target image, they use an autoencoder to generate a mask. And that mask and the target are fed back to the discriminator to check whether it's good mask or bad mask. Right? So if they have many training examples, they can make this generator very good at generating the OPC mask directly from the target. And on top of that, because they cannot achieve exact solution, so on top of that, once they have the generator to generate the mask, they also applied ILT, the inverse lithography transforms, to basically fine-tune that image to something that is actually useful. So that's the using the generator approach. Now talk about the optimization with reinforcement learning. One problem that is applicable is called the logic optimization problem. So basically for logics, you can construct logic with this thing called a majority inverter graph. What it does is the circuits can be represented in this graph. And the goal is to either reduce the area of the graph or reduce the depth of the graph, right? So in this case, it's a 3-level depth on the left side. So there's a transforms that you can apply to the graph such that at the end you will have shorter depths, right? So at the end, this is a depth equals to 2 instead of 3. So that's optimization. So we can map this into reinforcement learning problem. And just a short introduction of reinforcement learning problem. Basically, you will have a reward, right? In the game scenario, the reward is the score you scored, and you have states. And in this game, the state is the screen, and you have action, which is maybe move your objects left and right, and you have a action value function Q, which basically predict future total rewards on the current states and the action. And you can have a policy function that basically tells you the probability of which action to choose. And then you can use the policy gradient to train a model that's going to produce the probability of these actions. So in this case, let's say you have 3 actions, left and right and fire, then this networks is going to train a value, predict a value on whether you move to left and whether you move to right or fire, have probabilities that you can train. And now, how do we use this for optimization problem, right? So basically, we just need to map the reward function as logic depth reduction, right? So if I'm reducing taking a transform, if I'm reducing my logic depth from 3 to 2, now I have reward 1, right? And what is state? State is current graph, the current circuit graph. And we can use actually GCN, the graph networks, to learn the graph state. So basically, you have the embeddings on the GCN. And what's the action? Action is actually the transform you use. So for each given state, you can have only a limited number of transform you can do. So that's the action. And the policy is basically compute the probabilities of which move you take, which transform you apply to the graph, given that state. So that's how you transform the logic optimization problems into reinforcement learning problems. And that actually shows a very good results from that work. Okay, so I'm going to wrap up. Basically, I think there's a lot of interesting problems in the design automation areas that you can apply machine learning. But don't just create a problem for machine learning. I think they are good for these 4 type of problems. One is if the problem is intractable or with high complexities, high computation complexities. So that way, basically, you are saving computing power, right? If you take like days of the runtime, now it's machine learning model can inference very fast. And second area is things like if you don't have analytical solutions. So basically, you don't even know how to compute, right? If you don't know how to compute, how do you do it, right? So using machine learning. And third is like there are many conventional algorithms in design automation areas that use a lot of heuristics. Now you can use machine learning to replace those heuristics with basically a better heuristic based on the model. And then the fourth and the most exciting area is like, they call the really hard problems. I would say like AlphaGo is kind of a hard problem, and we have really hard problems in design automation as well, such as how to do analog design. All right, so conclusion is we think deep learning and machine learning can really improve the quality and productivity of design automation in many ways. I think the research should focus on apply advanced DL models to really hard design problems. And there's still a lot of challenges. We have dataset challenges. Unlike the other communities, the datasets are not open in the design automation, the semiconductor industry. And also, we have to solve model transferabilities problems, and also how do we interpret the model, right? Which is also very important. That's it. Any questions? Yes. Oh, I mean the training problem? I mean the training the model, how long it takes? Or inference. Oh, it's task dependent. Depend on the projects. Some if your data set is relatively small, then your training time is also very fast, right? But for example, the testability project that we did, the training time is like hours, right? Because we have a circuit that has millions of nets, millions of objects, and we are training for multiple designs. So that takes hours to run, right, to train. But the inference is very fast. So inference is like seconds, right? So that's one example, right? there are other examples like something, yeah. We usually don't have things like you have to training for several days. We don't have that yet, because that's unless we have really super big data sets, right? And yeah, so I would say ours is kind of the limit right now, right? Yeah.
Other than like productivity for your designers and developers, how much like efficiency or speed can you get out of the chip from like a completely novel design, say that a GAN came up with or something like that? Is there a lot of you can squeeze out of that?
Yes. So actually, productivity and the quality they are sort of like trade-off. So if you have high productivity, you can always fine-tune your design, right, with more iterations. So usually the chip is limited by the schedule, right? So I have to release this chip by the end of next year or whatever. So that means you cannot work on a lot of features. You can only do, you always leave features on the table. So if you have high productivity tools, then that means you have more chance to explore more design ideas. And from optimization point of view, there's also a direct influence of machine learning to the quality of results. For example, we can do using machine learning, like for example, the logic optimization project we talk about, that can directly optimize the design to a better point that cannot be achieved by conventional algorithms. And we can do design space exploration with machine learning, which means you can tune your parameters with machine learning that give you better space, better design point, basically. Right. So there's many different ways that you can improve the quality directly or indirectly with productivity improvement.
Where are the wafers produced? You chain here in Austin?
Sorry that I cannot answer that. Yeah, but yeah, it's basically there's only 2 companies in the world that can do fabs, advanced technology nodes. So you know where they are. So yeah. I'm sorry. What question again? How do I get the product team to adopt the methodologies? Okay, yeah, so we basically do some demos, like we showing this works, and then we work with them because product team has larger data sets, right? So we show the results on smaller data sets. We say, okay, this works, and you have larger data sets. We work together to build a better model, right? So. Yeah, and a lot of time we work directly with them, even at the start, because we need the data, and the other guys has data. So. Actually, it's not because actually the whole company is like kind of adopting the ML methodologies. So everybody doesn't matter what kind of design they're doing, which part of the organization they are working. They always want to try machine learning. It's like kind of like the new tool, right? Like, so everybody's trying it, and it's very easy to sell if you have machine learning. But it's difficult to prove that your model is better, right? So it's yeah. I think that the transferabilities of the models are very important because everybody can have a training data set and testing data set and saying, okay, my training looks good, my testing looks good. But are you actually covering the entire space? Like, is this model transferable outside of your data set? Right, those are the practical problems that any project has to solve. Yeah.
Okay. Any last question? All right.
Okay. Thanks for staying late.
Yeah. Thanks, Mark. That was excellent talk, especially learning that deep learning technologies and these machine learning technologies are being used in different domains. It's catching up everywhere. So that should be interest to you. And if you are specifically interested in this domain, how they are applied, I guess, Mark, you're accessible somewhere. Okay, I can post slides and your contact on our meetup group.
Sure.
Okay. All right, with that, we'll conclude today's meetup. And thanks for coming here. And hopefully we'll see you in the next meetup. And please do clean up after yourself if you can. Help us with that. And thank you.